All right, so I know that this concept is difficult to understand because it's pretty abstract. We're talking about things we can't even see. So I'm going to try a little simulation here where we're going to sort of let you see them. So I've assigned the little orange blocks as hydrogens, and a hydrogen has one proton in its nucleus, and so its molar mass, or its atomic mass, is 1 gram per mole. One proton, so 1 unit mass, 1 gram per mole. Carbon has 6 protons and 6 neutrons, which gives it a total atomic mass of 12 mass units. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And its molar mass on the periodic table is 12 grams per mole. Neon, just as another example, has 10 protons and 10 neutrons, which gives us 20 mass units and is marked as 20 grams per mole. Now, let's just do a visualization exercise where, let's say I've got relatively equal volumes for each of these, and Avogadro's concept said that if the volumes are the same, they're going to contain the same number of particles of any particular gas. So let's say that this particular volume contains 5 hydrogens, which means that it's also going to contain 5 carbons if we had carbon in gas form. Which, let's just bear with me here. We're just illustrating the concept. So I'm going to put 5 carbons into here. And also, the same space would have the same number of neon particles, neon gas. You light it up, it gets really pretty orange color. You see the neon signs? That's actually what they're doing. They're putting an electric current through neon gas and it lights up. Okay, so we've got 5 in each. Now remembering that 5 hydrogens are each worth 1. So 5 of those guys times 1 is going to give me 5 mass units, or 5 grams per mole. So the mass here is 5. When I look at the next one over, each one of these is worth 12. So I've got 1, 2, 3, 4, 5 times 12. 5 times 12 gives me 60 mass units, or 60 grams per mole. Now, neon's the last one, and I've got 5 groups of 20. So 5 times 20 gives me 100 mass units, or 100 grams per mole. So when I'm looking at these, I can see that this one is 12 times greater than this one. This one is 20 times greater than this one. So you can see that the ratios that exist here continue. As long as you've got the same number of particles, you're going to have them in the same ratios because they're all sort of based on that one base unit of hydrogen. Now, here's where we try to stretch it a little bit. If I wanted to have 12 actual grams of carbon, I would need a certain number of these carbon atoms to have that created. So I'm going to need a lot because each one of these is super, super teeny. So however many I'm going to put in here, I'm obviously not going to get as many as is truly there because if you remember the video on moles, the number of moles is ridiculously large. But I'm going to put a whole bunch more of these in here until I get to 12 grams. Okay, so yeah, now I'm just wasting time. So I got a bunch more in there. And let's say that I have now reached 12 grams. Well, if this is 12 grams, then I would have to have the same number of these little guys the same space, if I had the same number in the same space, then it's going to follow the same ratio. And the ratio is one of 12 to 1. 60 is 12 times bigger than 5. 12 is 12 times bigger than 1. So if I wanted 12 grams here, I would end up with 1 gram here, and they'd be the same number of particles because the ratio is being maintained. Now, if I went over here to neon, neon's a lot bigger, so it's going to weigh a lot more. And if I kept adding neon until I had the same number of neons that I have of carbon over here, and carbon weighs 12 grams, then, and hydrogen weighs 1 gram, I could go back to hydrogen, make the math a little easier. So now I've got all these neons in here. Same number of neons as I have carbons as I have hydrogens, so they should follow the same ratio. And my ratio was 20 to 1 here. So if this is 1, then this is 20 grams. So the whole mole concept is basically based around how many of these is in 12 grams. Because I know that these ratios follow, and I know that hydrogen, being 1 gram, is the smallest, lightest element on the table. So they used carbon because it was easy to work with, and they knew the relationship here. But in reality, everything is compared to hydrogen because hydrogen is the smallest. So if hydrogen is 1 gram and 1 proton in its base unit, and carbon has 12 protons and neutrons in its base unit, carbon is going to be 12 grams when hydrogen is 1 gram. And these are the numbers that correspond with the mass units. So it says exactly what it is. That's why those numbers are important. You've been taught to use the atomic mass to figure out how many protons or how many neutrons are in an element, because the protons and neutrons add up to the mass unit, which is the atomic mass. Now we're telling you there's another way that we can use that. If we blow it up to grams that we can actually measure, the ratio stays the same. So we know that when we're looking at the atomic mass or the molar mass, which is the same thing, then we have the same number of particles in 12 grams of carbon as we do in 1 gram of hydrogen or 20 grams of neon. And that's what a mole is. It's that number. It's like a dozen. Dozen's 12. A mole is the number of carbon atoms there would be in 12 grams of carbon, because this 12 grams matches the molar mass or the atomic mass of carbon. And when they first started working with it, they didn't know what the number was, but they did a whole bunch of experimentation, and it eventually came out to be 6.02 times 10 to the 23rd. That's how many particles are in a mole. So that's what this whole chapter is based on, is knowing that we can kind of play with these ratios and we can convert between mass, volume, and particle numbers, knowing this ratio relationship. So I'm going to go through some example questions with you about that, but hopefully this sort of visual gives you an understanding of what we're talking about when we're talking about moles and molar mass.